Okay, calculus. Chapter 12 starts with vectored value functions. Really, to cut to the chase, the definition of parametric equations we've used previously was two-dimensional, where x and y were determined by a function in terms of time. We know a space curve can extend that idea into 3 dimensions. Now, a new type of function, which is a vectored value function, can kind of demonstrate the same idea by instead calling it parametric equations multiplied by the unit vectors and the directions in either 2 dimensions or 3 dimensions. They can be denoted either with the eyes or in the same vector form we've done before. Now, a curve in the plane or space consists of a collection of points and is defined by parametric equations. 2 different curves can have the same graph. For example, these 2 have the same graph because it's still sine of something and cosine of something for each term. However, this one will cover the area much more quickly, and it gets faster and faster as it goes. Now, even though f, g, and h in these situations are all real functions, r of t, which is the combination of all of the functions working together, is a vectored value function. So sometimes they'll be referred to as scalar functions as opposed to vector valued functions. So what is the purpose of a vector value function? There's a few purposes. It lets the parameter t represent time and represent motion along a curve. Why is that helpful? Well, having a shape is nice, but knowing how the shape is traveling and the speed at which it's traveling can be useful. You can also use a vector value function to trace the graph of a curve. In either case, the terminal point coincides with a point xyz on the curve given by the parametric equation. So you can have a shape and know the starting and ending point, which still is the same thing as giving you the direction or how something came to be. The arrowheads along the curve that you can see over here indicates the direction it's traveling. So that way, if you're going to trace the curve, you at least know the direction you traced it when you're drawing it. Okay, and unless stated otherwise, the domain of a vector value function is considered to be the intersection of the domains. So the only way that the vector value function has a number in its domain is if each component has that number in its domain. Now when it says sketch the following plane and space curves, we have x equals 2 cosine ti. This means x equals 2 cosine t. Because remember, I is in the x direction. Y equals negative 3 sine t. Which means x over 2 equals cosine t. Negative y over 3 equals sine t. And remember, cosine squared plus sine squared equals 1, so this is actually an ellipse that goes out 3 in the y direction and 2 in the x direction. Now, one thing to note, not only does this have a shape, but it's supposed to have a direction. How do you know what direction it's going? Well, let's think about this. When t is 0, cosine of 0 is 1, so x is 2. So we're starting where x is 2 and y is 0. Now, let's think about at pi over 2. What's the cosine of pi over 2? 0. So x becomes 0. What's the sine of pi over 2? 1. So it means y is negative 3. So we're actually going around this circle clockwise because of the negative. So this negative flips the way we're going around the circle. Instead of going the direction we would normally go for the unit circle, it's actually going clockwise. Now you can try to draw these, but again, just like in 11.6, it's hard to draw 3-dimensional objects. So let's have a general idea of what's happening. For cosine t, so x has a radius of 4, y has a radius of 4. So we're talking about a circle of radius 4. But k doesn't have a trig variable, it's just t from 0 to 4 pi, which means that the height, k should be increasing to 4 pi the whole time. So we should be traveling along a circle. This should be the normal direction the circle goes, because they're both positive, so going clockwise. But as we're tracing the circle, we should be rising. So it should be something like, almost like a curl, but going up. So it's like going up a cylinder. And since it's a 4 pi, it should have 2 full revolutions, something like this. And we have an actual picture of it on the next page. So this is what it actually looks like. So this is the whole shape, and the line is our vector value function traveling on the shape. So it's like a helix along a cylinder. If we need to represent a general equation as a vector value function, the easiest way to do is set the variable of our choice to t. This assigns a direction to the shape, but different choices can go in opposite directions. As an example, take y equals x squared plus 1, let x be t. Then r of t equals ti plus y is x squared plus 1, so now it becomes t squared plus 1j. Another great thing about vector value functions is they're easy to add or subtract or multiply by scalars, because they're component-wise for all of those. Now, at some point, you probably assume calculus was going to come into play. The limit of a vector value function is just the limit of each component. If r is a vectored value function, in order for it to have a limit, though, all of the components must also have a limit. So it's basically saying take the limit of each component, and if they all exist, then the limit is the whole thing exists, and it's going to be that point. Continuity of a vector value function says a vector value function exists or is continuous at a point if the limit exists. So if all of the limits of the scalar equations exist, then the limit of the vector value function exists and it can be continuous. So to discuss the continuity of the following vector value functions at a given point, let's make sure at t equals 0, we take the limit of each one of these. The limit as t approaches 0 of t is 0. Here there is no t. Here it just becomes a squared. They all exist, which means vector value function should exist there as well. You might ask, is it this or is it this? The limit should be a point and not a vector, because at this point we're not traveling, it's asking about the specific point here. Now let's look at b. The limit as t goes to -1. Now, what do we know about -1? It exists here. It's an edge here. It's an endpoint for the second one. And here it's fine because it's squared. So we really need to take the limit as t approaches -1 from the right to be safe, because it's the domain of our whole thing is the intersection of the domains of the endpoints. And so this becomes -1, this is 0, and this one is 2. So it's the point -1, 0, 2. You could also call both of these in vector form. R of 0 equals aj plus a squared k. Here, r of -1 equals -I plus 2k. And that is it for 12.1.